Hey everybody, now that we have torque and the idea of net torque under our belts, let's look at how this applies to, frankly, what can be complicated problems. The topic for this video is known as static equilibrium. We may have actually used that term before, but it takes on a more complicated meaning now after we know about rotation, okay? So, static equilibrium, what does it mean? What's the definition? Well, if an object is in static equilibrium, that means it's not experiencing any translation or rotation over time. It is static, and it's staying static. Okay? It's not moving, and it's continuing to not move. Now, that doesn't mean there's not any forces or any torques acting on the object. It's that it must mean that any torques or forces are canceling out, right? Because if I have two forces that are totally canceling, well, the acceleration is zero. Likewise, if there are torques but they're canceling, well, there is no rotation that's happening. So this is kind of the three requirements here. Now, the first two things, we've done this, okay? If something is not accelerating, then the sum of the forces in the two directions must add up to zero. But now that we have a sense that also objects can rotate, if something is continuing to not move, if it's in static equilibrium, that must also mean that the net torque is zero. For example, and we're going to use this as kind of our main example, and a lot of problems will show up in this same kind of vein, okay? Think of like a simple teeter-totter. I don't know, maybe you find them at the park. But this plank of wood is set to balance on this fulcrum. Here is our hinge right here. Well, if it's just at rest, nobody is on it, it's in static equilibrium. In fact, maybe even when this dog is standing right here, just for this moment, it is still in static equilibrium. All the forces, all the torques are adding up to zero. You could probably imagine, especially if this dog kept walking this way, that the teeter-totter would, start rotating. That would be when it's not in static equilibrium, okay? So we're looking at a particular circumstance where the net forces and the net torques on objects are equal to zero. Now, before we get into how you solve these problems, we need to quickly revisit the idea of center of mass. Now, you should already know what that is. It's kind of just an average, right? It's the center point, or so to speak, it's the general location of where the average mass is located for an object. For now, though, or now moving on, there's another way to think about it because it has to do with rotation. The center of mass for an object is its balance point, where if you were able to support it at that location, the object would balance. For example, let's say I have, I don't know, maybe this is a metal bar of some kind, but it's nice and evenly distributed, okay? That means, and you could probably imagine this, doesn't take too much to think about, if I had my hinge right in the middle, well, it's likely to balance at that spot. My little pen right here is pretty well balanced. I can't do it on my fingertip. But if I put it on the middle part here, it would probably get pretty close to balancing right there on my finger. Now, let's see on this diagram, if it was uneven, we don't come across this very often, but if there was more mass going this way, so it's pretty light over here, but it's heavier, maybe it's denser over here, okay? If it's more dense over here, there's more mass, where would the balance point be? Well, the average location is kind of cheated over to this right side. I would want to put a hinge or maybe a balance point right here. That would balance it. This mass here, more or less, kind of balances with this mass right over here. Oh, so when you think of center of mass, because all objects have a center of mass, yeah, it's the average location, but it's also where the object would balance from, okay? For the most part, we are mostly dealing with this scenario, where the object is pretty uniform, so the balancing spot is right smack in the middle. Okay, let's say I have an object that's in static equilibrium. How do I approach it from a force and net torque perspective? Right here, I actually have pretty much the same strategy that we saw when looking at the net forces when applying Newton's second law. But there are a couple key differences, so let's quickly go through them. Number one, draw a free body diagram, but in the past, we would just draw a dot, right? Now, because we're dealing with torques, the direction, or I should say the location of the forces matter. So if I was doing it for maybe that object I showed in the last slide, your free body diagram should actually take the shape. I sketched a quick little outline of the object. And then I can see, oh, okay, there's a force right here. I'll call that F1. There's a force right here. I'll call that F2. There's a force right here. So now I know where the forces are acting because if they might be applying a torque, I could figure out maybe clockwise, counterclockwise, all that good kind of stuff, okay? So now actually sketch the object so you can see where those forces are acting. Next, pick a location for the hinge where the object is going to be rotating. Again, especially if it's nice and uniform, usually the hinge is going to be right in the middle. And also, a lot of times in the problem, it's going to tell you, or it's going to be super obvious where the hinge is. Like if there's a teeter-totter problem, and it says it's balancing on this little fulcrum, this triangle, bam, that's probably where you want the hinge to be, okay? Now, there is a little bit of a cheat, okay? If you're really keen on things, you could recognize that, wait a minute, torque is always R times force. It's the force times how far away R is. R is that hinge. It's where the object is located. So if I maybe drew this a little better, if F2 was right on this hinge here, let's say I had no idea what F2 was. If it's located at my hinge, well, R would be 0. So if there's a force that you don't know the value of, ooh, a little bit of a cheat. We won't see this all the time, but it might be helpful if you put the hinge in that location. Well, there wouldn't be a torque from it. And then that would just eliminate an equation or a term in your equation, okay? You'll see that in practice. Number 3, we have to identify our positive and negative directions. Now, we're dealing with forces and rotation. So a very common thing that I like to draw, and you see this a lot also in textbooks and from other physics professors, is something like this. I don't know why, but I really like drawing this. Ah, look at that. What a work of art there. This is saying upwards is positive, which we normally do. Rightwards is positive. And what is convention? Counterclockwise is positive. Ah, there I've clearly labeled my positive and negatives. And then this is really more or less what we've done before. Set up the sum of forces and the sum of torques. Especially since we're in this rotation unit, I highly recommend when doing these problems, you first try this. Try setting up the sum of the torques. Okay, usually that's the best bet to start being able to solve for things. You don't have to. You could solve for the sum of the forces to start. But normally, if you try here or you try here, you'll realize you'll have too many unknowns and you'll have to try something else anyway. Okay, often if you start with the sum of the torques, that's the most efficient way to solve these problems. And then we're doing algebra, right? Write out what the sum of the torques are, set them equal to 0, right? Because none of these things are moving. It's static equilibrium. Set all these equal to 0. And then try and solve for whatever it is you might be looking for. All right, now I'm going to go over a very general example problem. There's not going to be any numbers or anything. It's going to look kind of like an algebra mess, but follow along as I work us through the process because these are challenging, especially at first, okay? So here I have, again, kind of that teeter-totter. Let's say I have a bar and I have two masses just attached to the ends of the bar. And the diagram is really hinting. It's balancing right here. We're going to use that as our hint, but it's balancing right here. Now that's not in the middle of this bar. Sometimes it'll be right in the middle, but it's not right here, okay, in this picture. You also might hear in problems that the bar is balanced or that the bar is in static equilibrium. That, of course, just means that we can set up the sum of things equal to 0. Also, sometimes you might see the phrase ignore the bar's mass or the plank's mass or whatever it is. That just means what it sounds like. We'll say that it has no mass. I'm not actually going to do that in this example, but that's pretty common. It makes your algebra life a little easier, okay? We won't do it here, but you might see that, okay? Let's go through our steps. Step number 1 was to draw a free body diagram for this scenario. I've already drawn the bar. I did that ahead of time to save myself a little time. What forces are acting on this bar? Well, there's this mass, and I've labeled that M1. So there's M1 acting downwards. Bam, M1 times G, that's the force, okay? Now, if this bar does have mass, and if it's uniform, okay, it'll usually say it's uniform, so that might also be something you see, uniform. If it's uniform, where is that weight acting? Right in the middle. So I'm going to put the weight right in the middle. Maybe I'll call that the mass of the bar times G. There's also this thing right here. There's the mass 2 times G. Any other forces? There is. This bar is sitting on a balance point. This is my hinge, but that's exerting an upward force. What kind of force is that? It's a normal force. Oh my gosh, students often forget that, okay? Now, it's labeled that from the hinge here to here, that's L1. From the hinge to here, that's L2. You know, I kind of made up this mass of the bar. We're not going to plug in any numbers, but you might also need that distance, right? Okay, I'm going to call that just R for the sake of this video. Okay, because when we're looking at torques, you need to understand both masses and forces and distances. But that's number 1. There's my free body diagram. Okay, what's my step number 2? Step number 2 is all about the hinge. Where's my hinge going to be? Oh, I'm going to slap it down right here. And it's super obvious, right? You don't necessarily have to put this on your paper, but make sure in your brain you know where your hinge is going to be located. So there's my step 2. Okay? What about step 3? What are going to be my positive and negative directions? I like to just follow convention. So I'm going to draw this. Any forces that are up or to the right are positive, and any torques that are going counterclockwise, I'm going to call those positive as well. There's step 3. Okay? Step number 4. Let's now try and write the sum of the torques. Okay? Are you ready? Take a deep breath. For 4, let's write out the sum of the torques, the sum of the forces. My hint was to start with the sum of the torques. So that's how I'm going to start. Sum of the torques. Okay? First one. What's the first torque you imagine right here? Well, this M1, that's going to be exerting a torque. So there's torque 1, tau 1. How about the torque from the weight? Okay, so I'm going to have tau bar. I'm not going to add any pluses or minuses yet. We'll do that when we figure out direction. Okay, so this force is exerting a torque. I record it. This force is exerting a torque. I'll record it down here. This force, yeah, sure. So there's the torque from 2, this mass 2. And there's another force. There's the normal force. When I add them up, whether they're positive or negative at times, they're going to add up to 0 if it's in static equilibrium. Okay, now let's put in whether things are positive or negative. This torque right here, okay, I like to sometimes even take my pencil and I imagine things rotating, okay? My hinge is right here. This M1 is acting like this. Is it going to make it rotate positive or negative? It's going to rotate in the positive direction, counterclockwise. So that's positive. The torque from the bar, if my hinge is here and the weight is right here, notice, the hinge is here, the weight is right there. That's going to make it rotate this way, this way, this way. That's going to be a minus. This force here, similarly, minus. Okay, the normal force, gosh, I'm not even sure. Maybe I'll put plus for now. I'll come back to that. So what's tau 1? It's the force. The force is going to be M1 times G times the distance from the hinge. M1 is here. The distance is this. That's what this L1 is. So I'm going to put L1. Minus the bar. That's the mass of the bar times G. I kind of made it up, but that's R. Okay, again, the distance from the hinge. Minus, now, okay, this guy right here. M2G, that's the force. But I need the length. From the hinge is right here. That's what this diagram is. That's L2. From the hinge to way over here. So that's L2. Now this normal force, man, I wasn't even sure if it was positive or negative, but notice, the normal force is where the hinge is. How far away is the normal force from the fulcrum? It's 0. It's no distance away. The distance is 0, so that's the normal force times 0. Oh, that's just going to cancel out. That equals 0. So this is my setup. M1G times L1 minus the mass of the bar times G times its distance away minus M2 times G times L2. That equals 0. Again, there's no numbers to plug in, but there is my equation. Again, don't forget those distances. Now, maybe you don't have enough information here. So what would be your next step? Well, I don't know. Maybe you try writing the sum of the forces. There's nothing horizontal. Maybe you try writing the sum of the forces in the y direction. So that's going to be, let's see, I have all these forces that are acting downwards minus the normal force. So normal force minus M1G minus M2G minus the mass of the bar times G. That would all add up to be 0. That's at least a little more normal. But okay, follow those steps again. Free body diagram. Notice, it takes a long time, but if you go slowly and if you're methodical, they're not too bad. You're doing the same kind of recipe, same chop and onions once you get a couple of these under your belt. But they're definitely tough. So take your time, follow the steps that I had right here, and it'll make sure you stay nice and organized and you don't get tripped up and you'll be able to solve it. This is probably the most algebra intensive of all the little videos in this sequence, okay? Well, maybe not, but it's definitely tough, but it's not always going to be this tough. Okay, kind of a long video. I'm done. Thanks for watching.